Okay, in this video I want to briefly talk about the properties of vector operations and the idea of vector spaces. So I have them written out here, and these are also in the textbook, but we're going to let V, U, and W be vectors, and we're going to let B and C be scalars. And so this is kind of all the properties of vector operations on one another and scalar and vector operations together, and they are similar to things that you would use in just regular algebra when you're dealing with just numbers. Okay, but they're involving vectors. So the first one is that U plus V is equal to V plus U. So vector addition is commutative. You also have U plus the quantity V plus W is equal to U plus V, that quantity, plus W. So it's a, this means vector addition is associative. You can group them together in different ways, okay, and that's okay. So vector addition is commutative, and it's also associative, just like regular addition. Also, there's a zero vector, and we're going to let that be 0 with the vector over it. And it's just basically, for the type of vectors we're using, it's just 0, 0, okay? And so basically what this is saying is that 0 is an additive identity. So you can take V plus 0 and you'll get V. So there's an additive identity for the vectors. And then also, if you take the scalar 1 and multiply it by V, you'll just get V back. And so, in a sense, there's kind of a multiplicative identity as far as the scalar is concerned. Okay, a scalar of 1 times V is equal to V. Notice that there's no multiplication with vectors. There's only addition and scalar multiplication, but there's no way of taking two vectors, multiplying them together to get a third vector. Okay, and so also if you take 0, the scalar 0, and multiply it by V, you'll get the 0 vector. Okay, and so this is saying that for every vector V, there's an opposite of V, and it's basically where you have the opposite signs for the components. And if you add these together, you get the 0 vector. So every vector has an additive inverse. And then these last ones here are properties involving scalars and vectors here. So this is saying if you have a scalar times a vector, that quantity plus a scalar, so B times the quantity, C times V quantity, then what I can do is I can group the two scalars together and then multiply the result by V, and I'll get the same thing. Okay, so there's kind of this there's this associative property involving scalars and vectors, is what that is saying. And then there's a distributive property. If I have two scalars being added together and I'm multiplying that by a vector, I can distribute the vector over the scalars and I get B times V plus C times V. And you can also take a scalar and multiply it by the sum of two vectors. So B times the quantity U plus V. And then what I can do is I can distribute the scalar over, and I would get B times U plus B times V. So you got these two different distributive properties. Okay? Now, all these properties, as you work with vectors, you can take advantage of all these in different ways. But there's a deeper thing that is at work here, and that is this idea of vector spaces. Basically, if you have a set of vectors and a set of scalars, any set of vectors and scalars, such that these properties hold, then you would say that it is a vector space. Okay, and this is a real abstract thing, because these vectors don't have to be these components with, you know, 2 numbers in there. They could have 3 numbers or 4 numbers or 10 numbers. And if all these properties hold, you would get a vector space. And the other interesting thing is they don't even have to be a list of numbers. They could be a list of functions. So there's a way, if you can define these operations and all these properties hold, you would still have a vector space, but these would be functions and these would be numbers. And you'd get this vector space, which is kind of weird, but the solution to a differential equation is actually a vector space. Okay, you would find the basis of the solution, a couple functions, and then that would generate an entire space of solutions. And so you get this abstract concept that really forms a foundation for many other branches of mathematics. So this idea of vector space is really important. We're not going to be doing anything with vector spaces or anything like that, but these operations or these properties of the operations are important, and there's a list of them right there, and all together they form this idea, this concept of a vector space.